will go ahead and share my screen first. All right, this is working. All right, great. Well, thank you so much, Kate, and also Keith, for the invitation to present here today at DREAM, as well as the Power Energy Series seminars. It is a great pleasure for me to talk to you today about some of the work that we've been doing recently on designing learning algorithms for pricing demand in safety critical infrastructure systems. And as you just pointed out, most of the work that I do is motivated by this exciting transformation that we're seeing in our power systems with the introduction of grid scale and distributed renewable energy resources, particularly at the distribution system level, transportation electrification, introduction of storage devices, as well as increased customer engagement in how we balance demand and supply in our power systems. So that last point is basically what motivates this talk. The idea that we can manage electricity demand more actively in order to balance supply and demand came because we started seeing the integration of automation systems, including Internet of Things, smart appliances, home energy management systems, and so on in people's homes. And so the idea is there could be an electricity retailer or an aggregator that can sort of characterize how flexible a population of electricity customers are in their electricity demand and sort of tap into that flexibility in order to better balance supply and demand in the power grid in real time. The challenge is that demand is a complex object for which we do not have good characterizations. And the infrastructure system serving this demand is safety critical, meaning it has all these reliability requirements that cannot be violated. And so very, very, very broadly, since this is not a power and energy series seminar necessarily, I want to tell you sort of what are the different forms of demand management that have been proposed over the years. The first category is employing centralized control strategies. So basically customers specify to the aggregator how flexible they are in consuming consuming energy through certain appliances in their homes. And then the aggregator kind of takes over control of that appliance. This requires uplink from the customer to the aggregator, meaning communication from the customer to the aggregator to specify exactly what their needs are. It violates the customer's privacy potentially, and also requires proper design of mechanisms to incentivize customers to participate in such programs. Then kind of to see perhaps whether we can address some of the downsides of such mechanisms. There's on the other side of the spectrum, distributed network utility maximization type mechanisms that try to get the customers to collaborate with each other to together achieve sort of a certain supply goal. So you want to together consume a certain amount of renewable energy production, and you use distributed optimization to achieve this goal. It still requires uplink from the customers to the aggregator, as well as these agreements to collaborate together to sort of achieve these goals. And so both of these are rather complex to implement if you think about it. And so the other sort of perhaps more easier to implement mechanisms try to basically use simpler solutions that don't require customers to communicate their characterizations of their demand flexibility to the aggregator. So instead, they want to just estimate or learn how flexible the customers are through repeated interactions. So these type of mechanisms were first sort of made popular for thermostatically controlled loads, and like your air conditioner, used either for emergency load reduction since the 70s, or for more sort of newer applications to follow certain supply profiles, perhaps renewable energy production profiles or something like that. But what is actually more relevant to the work I'll be talking about today is how these learning algorithms are being used to learn how to shed electricity demand during emergencies. So let's say I have a number of customers, and I can call on them to reduce their demand because there's an emergency currently going on in the power grid, right? How can I learn which ones will respond to such a signal, because customers may not respond to a request to reduce their demand. And I need to have a characterization of who will respond and who will not in order to be able to run the power grid during an emergency. So these learning algorithms kind of look at emergencies. What I want to look at today, however, is a little bit more. I want to see whether I can design so-called dynamic prices for electricity that can get the customers to shift their demand around to different hours of the day. And for example, in this picture that I have taken from somewhere, this is not my picture, I'm trying to decide which one of these 4 tiers of pricing can I assign to each hour of the day, right? In order to get the customers to shift their demand around to times when the grid is under less stress and there's more supply available. Now, I don't know how customers are going to respond, right? And I don't have a way of communicating with them aside from learning how they respond through repeated interactions where I post a price, I see how they respond. Again, I post another price, I see how they respond, and so on, right? And so the setup, and just to repeat, is that say I'm an aggregator and I don't have a price response model for the users, I want to learn it. My goal, of course, is to use dynamic pricing to minimize my costs. The problem is I cannot, because I don't have a model for how customers respond to my dynamic prices, I cannot hope to minimize my cost on day one. So instead, I focus on minimizing my cost perhaps over a year, right? And so I want to minimize perhaps my daily cost over an entire year. And there's also a constraint that I cannot blow up the power grid in the process of doing so, right? And so those nice equations Keith has behind on his board, I cannot violate them, right? So the idea is if I just apply a general purpose learning algorithm, I might post prices perhaps that will get the customers to shift their demand all to 6 p.m. and that could end up violating the constraints of the power system. That is not what I want to do. And so my question here is what type of mathematical tool may address such a problem? And the tool we adopted and I'm going to talk about in this talk is stochastic bandit optimization. And so if you're not familiar in stochastic bandit optimization, you have a learner that plays a game against the stochastic environment. So this environment has an unknown reward function, f of x, that the learner doesn't know. Each day she chooses an action xt and observes a noise perturbed version of that function f of x at point xt. And her goal is to minimize her regret of not knowing this function f of x over t periods. And so because we're talking about reward here, not cost, like I was in the previous slide, you want to maximize this accrued reward. And your regret is defined as the difference between the maximum possible reward you could possibly accrue, which is given by the maximizer of that unknown function f of x. So you select f of x star, that's the optimal action, minus f of xt, the actions chosen by the learner. Everything here is the expected reward, of course. There's a strong literature on this topic that I'm not going to review, but there's a lot of results here, both for parametric forms of the function f, where all the uncertainty in f is characterized by an unknown parameter vector theta, and also non-parametric models, for f that I'm not going to talk about today. Now, the variants that I used in this work that I'm talking about today, it focuses on this, variation of this problem where the learner is still interacting with an environment with an unknown reward function f of x, but the environment also has a set of unknown constraints, gi of x greater than hi, that the learner wants to not violate, even though she doesn't necessarily know everything about the function's gi. So every time she selects an action xt, she observes a noise perturbed version of f of xt, but also noise perturbed observations on the constraints that she's going to use in order to estimate those constraints. So her goal is still to minimize regret, the difference between maximum possible reward and the reward she's obtaining, and also to respect those constraints at all rounds. Because even though, for example, I don't know how customers are going to respond to my posted prices, I still don't want to blow up the power system. That's one way you could think about it. Of course, in this form that I am showing you here, and this is too general of a formulation and it's impossible to do much. So we're going to have to assume some structure here in order to start showing some results. So are there any questions up to this point before I proceed? Cool. So what I'm going to do is I'm going to show you some of our results where first we kind of restricted our attention to reward functions that are linearly parameterized by a parameter vector theta that is unknown, and also several forms of affine constraints that I'm going to show you. Of course, those of you who are familiar with the power system would know that with such a structure, it is very hard to do very realistic forms of dynamic pricing in power systems. And so I'm going to show you sort of safe algorithms with high probability regret guarantees that we devised for these simpler sort of setups. But then we're going to go back to perhaps what we could have done for the power grid setup. And there you'll see that the results that I have are not as theoretically strong, perhaps, but they are showing you perhaps some insights we get on safety, as well as show some type of algorithms that could practically work well. All right. So first, we're going to look at the first part, which is, as I said, just linear payoff structures and affine constraints. So in case you don't know, if I have no constraints, the problem that I showed you is the linear stochastic bandit problem. So no constraint. This is the original setup of the linear stochastic bandit problem. I'm going to assume that my actions lie in a convex compact set in RD, and that the payoff structure is the expected payoff of the action X is theta transpose X. Well, theta is unknown to the learner. So at each time t, or at each round t, I play an action xt and observe a noise perturbed version of theta transpose xt. And so the algorithms that I will be building on today all have this next step where, of course, they're going to use this information that they're getting from all these observations to build estimates on this unknown parameter vector theta. So once you receive all this reward information, you can create a regularized least square estimate for theta, which we're going to call theta hat t, and a bunch of corresponding confidence regions, CT, within which theta lies with high probability. So the guarantee is that the true parameter theta is going to lie in these shrinking confidence regions that I'm showing you here below with high probability at all rounds of the algorithm. So this is sort of the original setup. And now the question is, in the original setup, how should the learner choose XTs to guarantee good regret? So I'm going to show you two sort of famous heuristics for this problem. Again, still no constraints. So this is just basically a lit review. The idea is at each round t, the learner has access to this least square estimate, theta hat t, and the corresponding confidence regions. And so how there are one very well-known heuristics for this relies on the principle of optimism in the face of uncertainty. So it says at each round, pick the action XT that would have been optimal in the best possible environment that lies in the confidence region. So you see we're solving a bilinear optimization problem where we're choosing essentially the action that's the best possible action in the best possible environment. And this is called the UCB algorithm. And then the second sort of heuristic that we're going to build on today is Thompson sampling. It's originally a Bayesian framework, but here we're going to look at it from a frequentist point of view, meaning that each time we're going to take the least square estimate, we're going to randomly perturb it according to a Thompson sampling distribution that's given in the literature. And you get a randomly perturbed parameter theta tilde, and then we're going to choose the best possible action for that environment, theta tilde. That's Thompson sampling. Now, the order of regret of these two these two heuristics has been computed in the literature. The first one is square root t log t, second one square root t log 3/2t. And these are the papers that you can look at in case you're interested for these results. And now I want to go back to the problem that I was talking to you about, now that I've told you about the famous heuristics that can be used on the original problem. So still we're keeping the linear structure in the payoff function, but we're adding these affine safety constraints. So I'm going to show you one example of this affine safety constraint that we have explored. So the example is, let's assume I want theta transpose Bx to be less than equal C at each round t. I don't know theta, but I do know the rotation B and the scalar C. Okay, so every time I select an action X, I want this constraint to be satisfied. The challenge, of course, as all of you can see, is that if I don't know theta, I cannot determine if the action X is safe or not. So this is going to be a challenge that we're going to see in all the scenarios that we have explored. And so what I want to show you is that this idea that lies at the heart of all the algorithms that I'm showing you is that we're kind of creating these conservative inner approximations of the safe set using the confidence region. So it's a very simple idea in that, you know, I have these, I don't know what this, whether my action X will satisfy this constraint or not, but I do know that theta lies in this confidence region CT, right? And so if I ensure that my action X satisfies this constraint instead for all the thetas that lie in the confidence region, then I can say with high probability that my action is going to be safe. So what I'm showing you in this figure is that I have confidence regions within which theta lies, and also for the safe action set that I'm showing you above, the estimated inner approximations for each of the corresponding confidence regions, right? So what I want you to notice is that at the beginning of the algorithm, so this is the actual safe action set that I don't know, now highlighted in red, right? I don't know this safe action set. The optimal action X star lies at the corner of it. Let's say that's the case, right? So the problem is that now for the largest confidence region I'm showing you on the left, the inner approximation is now this purple region, the inside of that purple region that I have highlighted. And if you notice, the safe action set does not include the optimal action. So the optimal action will not be deemed safe to play by the algorithm in the beginning, at least iterations of the algorithm that we're going to use. The problem with this is that once the optimal action is not deemed safe, the learner will start incurring this additional regret, which we're going to call the regret of safety. And so that's what we basically want to characterize. Okay, so any questions up to this point?
Just one quick question. Do you just assume Gaussian noise or not?
Yes, yeah, all of our noises are R sub Gaussian.
Okay, great, thank you.
Any other questions?
So the constraints here would be, for example, a grid line flow constraint if it were applied to a power system, though they're general. Correct?
It kind of, we tried to sort of make it resemble grid constraints. Yeah, if you could see it, perhaps it was trying to be like DCOP type of constraints, but not really. So yeah, I mean, you have to really simplify the problem to fit this framework. So I don't have a claim that these frameworks can really solve a real grid problem. We're trying to see whether we can devise safe algorithms for simpler cases before kind of moving on to those more complicated constraints like grid constraints.
And it's just a linear constraint. Is there anything that makes it less general than that?
No, what you're going to see, we're going to have specific forms of these affine constraints for our result to work. And as we vary the form of the affine constraint, in fact, we have to vary the algorithm.
Okay, got it.
The algorithms are very specific to the form of affine constraint that we're going to have. This is one of them. I thought it's just one example to show you sort of this idea that you need to estimate the safe set. But I'm going to show you the 3 different cases that we have looked at for the affine constraints. Any other questions? All right, cool. So I just want to show you what happens if we, for example, naively change one of the heuristics that I showed you to instead just work with the estimated safe set. So if you remember the UCB heuristic, pick the best possible action in the sort of best possible environment. It was optimistic in choosing which environment could be plausible. And so a naive extension of this algorithm would basically say, well, just optimize for the best possible environment and also the best possible action instead in the estimated safe sets, as opposed to the original sort of known set of possible actions that we had. This is just a simulation to show you that this algorithm would get linear regret, and so is not desirable. We want sublinear regret. Why did this happen? The reason is, if you look at it, you'll see that in the estimated safe set will not expand properly, with this algorithm, because it does not explore the environment sufficiently. And so what we did instead is, I'm going to show you several results we've had for these constraints, where we have sort of at least modified how this naive heuristic approaches this in order to get sublinear regret. And then I'm going to show you the corresponding results we have. And then we're going to go back to the power grid problem towards the end, and so see our results for that. So just a reminder, any algorithm we propose, which is going to be, as I said, modifications of the UCB or Thompson sampling algorithm, cannot beat the regret guarantees or the orders that I have listed here, because these are basically the regret guarantees you can't have with a known set of safe actions. Just to start with, the first scenario we have looked at is this basically the simplest scenario we had. And that is, okay, the reward is just theta transpose X, and the set of safe actions is either theta transpose X less than equals C, or you can have a different parameter mu transpose X less than equals C, and you get noisy observations on mu transpose XT every time you select the action XT to play. And so for this case, we're going to have some standard assumptions also that I'm not going to go into, but these are pretty standard. And so what does the algorithm look like? The algorithm looks pretty much exactly like the original linear Thompson sampling algorithm. So what it does is it wakes up every day and creates the least square estimate and the confidence regions for the unknown parameter mu and theta. Just for the unknown parameter mu, it creates confidence regions and the confidence regions and least square estimates for theta. And it creates these inner approximations that we talked about for the safe set. And then it perturbs the RLS estimate with some noise, and that noise should come from a proper distribution for the Thompson sampling noise. And then it chooses the best possible action in that environment, plays it, gets this feedback, and continues. So this is exactly what the original linear Thompson sampling algorithm would do in this case, except what we had to do is we had to properly modify the noise distribution to ensure that this algorithm would explore properly and expand the safe set as a result. And so if you look at our results, you see that we were able to basically get regret guarantees that match the result of the original linear Thompson sampling algorithm without any safety constraints. So basically, if you look at the picture right here, the blue curve is basically our algorithm, and the red is what happens if you give the set of safe actions to the original linear Thompson sampling results that were provided in the literature. So this is the first setup. And the second setup is in fact what I showed you, is when we have the safe action set be this set of theta transpose Bx less than equals C. Again, a standard set of assumptions on this problem. However, in this case, our results are not as sort of general as the one I had in the previous case. Here we had to define a critical parameter, which we call the safety gap, which is essentially the amount of slack we have in the constraint at the optimal action X star. So the difference between C and theta transpose B X star is called the safety gap. And so our results do depend on this parameter. Our regret guarantees do depend on this parameter. For instances where delta the safety gap is strictly greater than 0, we're able to achieve the same order of regret as the original UCV or Thompson sampling-based algorithm. But for general safety gaps, which includes delta equals 0, we can only get a worst case regret of order t to the power 2/3 log t, which is not as desirable. All right. And then the last scenario we've explored, and I know I'm going a little bit fast, but I want you to see is that, that form of the affine constraint really sort of matters in the design of the algorithm. It's not sort of as general as one would like. Perhaps if you want to extend it to something like the power grid, this could become much more complicated, of course. The safe action sets that we have looked at in our third scenario are a little bit more sort of contrived, but they're actually motivated by a set of papers that appeared in the literature that looked at designing policies that can be used by a company perhaps that already has a baseline way of selecting their actions. So let's say I am a company, I have a way of doing things, and I have a baseline set of actions that I want to use every day, and they result in a certain amount of expected reward, RBT, right? And so I'm asking whether now this algorithm designer can come up with a way of making sure that I can increase my reward, where every day I'm guaranteed to receive an expected reward that is greater than a certain percentage of what the baseline action would have given me. And you could think sort of in a situation like, an electricity retailer or anyone who already has a certain way of doing things and guaranteeing things for people. This could be a way of ensuring that people don't really get pissed off if I go ahead and deploy a learning algorithm that can sort of change the way things are for people. So this is sort of the third scenario we've explored. The algorithm is a little bit different. It does use the same principles as the ones we talked about before, creates these least square estimates the set of safe actions. In this case, this is a Thompson sampling-based algorithm. We also have a UCB-based algorithm. So it does create this randomly perturbed version of the least square estimate, but then it checks this condition where if the minimum eigenvalue of the Gram matrix of all the actions that I've played so far is greater than a certain threshold, then it plays the action that the Thompson sampling is suggested. Otherwise, it plays a noise perturbed version of the baseline action. So that's sort of the idea of this algorithm, basically. And in terms of theoretical results, we're able to show regret bounds of order square root t log 3/2t for Thompson sampling and square root t log t for UCB. Again, these are the best possible cases we could have achieved for these two algorithms. And so these are the three sort of theoretical scenarios that I wanted to highlight in order for you to see that we're exploring, solutions that could have nice theoretical guarantees. But when we sort of go back to the power grid problem, the type of results we're showing are still sort of further away from nice theoretical guarantees that we could expect perhaps in simpler setups. So I want to show you sort of what the original problem was and how we approached it. This is sort of a transactional smart grid paper that we published in 2020, where we looked at this original setup where there's a retailer who wants to minimize their total perhaps annual costs, and they also don't want to blow up the grid in the process while learning about how customers respond to prices, right? So this is sort of the setup that paper looks at. Every day. The retailer posts a price that's a vector for different hours of the day. There's one price and observes how customers respond to this price basically after ex post, right? So customers do their thing, and through the smart meters, I observe their demand. Also, daily conditions are changing every day. The wholesale prices are changing. The renewable energy availability in the distribution system is changing, and so on. So every day, perhaps the optimal response that I want from the customers is changing, right? So my goal, if it was just a single day thing, would have been to minimize my cost on that day. And my cost depends on the demand as well as those sort of daily conditions that are changing. The problem is, of course, I cannot do that, right? I don't know how customers respond to prices. And also I don't want those operational constraints of the grid to be violated. So what we did is we used the variant of Thompson sampling for this problem. And why? The reason is that Thompson sampling is well known to perform well in situations with complex cost functions and sort of especially nonlinear cost functions like what I have here. And so the rest is mostly empirical. There's some theoretical results in the paper, but I'm not going to highlight them because there's a lot of conditions I have to go through. That's hard to sort of show in a presentation. There is a little bit of a trick in that paper in that, there's still, I want to sort of boil down the uncertainty in the customer's response to a not knowing a single parameter vector, theta. But those who are familiar with this might know that that's really sort of not perhaps that straightforward. We did exploit some sort of degree of knowledge that we have about how, customers sort of optimize energy consumption in their homes. So say if I have a bunch of smart appliances like electric vehicles or dishwashers and whatnot, if I receive a price and I have specified perhaps a deadline for charging my electric vehicle or running my dishwasher, then it's very easy for a home energy management system to know when to shift my demand to in order to minimize my electricity bill. So that's a very easy optimization problem for the home energy management system once they know my preferences, right? And so perhaps we could exploit the fact that things are automated in the customer's home to think, well, if I knew what are the preferences of the customers, then I would know what happens, how each of these different classes of loads will respond to a certain price signal. The problem is I don't really know how many of these appliances are in customers' home. I don't know how many electric vehicles have to be charged by 8 a.m., how many by 7 a.m., how much charge are they going to want, and whatnot. So what we rely on is this clustering of flexible loads in customers' home into a limited number of clusters. And for each cluster, we're going to assume we know how the appliances in that cluster are going to respond to the prices. And now then the entire thing becomes, can I learn how many of these appliances we have in each of these clusters? That sort of becomes the task. So if I knew how many appliances are in each cluster, I can sort of write down how all of these people will respond to my posted price PTAP. Problem is, I don't know. And so what we do is we want to sort of boil down the learning problem to learning about how many appliances are in each cluster. So what we do is we had a project to run surveys to learn about preferences of customers to pricing signals and so on, and we were hoping we could have so much data that we can create these parameterized distributions for sort of how people prefer to use their appliances. That was extremely hard. That was very experimental, and there were so many roadblocks that we ended up actually not getting the data we wanted to actually test this model. But this is basically the assumption that's in that paper, that there is distributions that parameterize how customers are going to want to use perhaps their electric vehicle or their dishwasher if prices vary during the day, right? And then after that, we basically deployed a Thompson sampling-based heuristic with some linear distribution system power flow constraints, sort of as the safety constraints in this optimization. And so in this setup, as I told you before, formal regret guarantees are limited to special instances when the parameter that we're trying to learn, the parameter theta, is sufficiently separable from all other possible scenarios for all possible scenarios for the parameter under all the prices that we can possibly post. So that you can see sort of is a very sort of, it's a strong assumption. So we're not claiming that, the theoretical results we have here are really sort of applicable to all possible scenarios that can happen in the power system. How the algorithm works is that it has a Thompson sampling distribution every day. It samples a parameter theta from that distribution, observes all those daily exogenous parameters that I mentioned, including wholesale prices, renewable energy availability, and so on. And then it sort of optimizes the cost for the parameter that was drawn, except that the constraints now take into account all the other scenarios that theta could also sort of be, all the other scenarios for the true parameter theta, kind of in line with what I was showing to you before. But again, I don't want to go into the details here. Once it posts the price, it observes the demand, and then it updates also. There's a posterior update on the Thompson sampling distribution according to the observation that we have. And then the algorithm kind of proceeds. Here are the regret guarantees we have when we tested this on a 30-node radial distribution system. There is a slight difference between what these algorithms do and what the algorithms I showed you in the first part of the talk too. There is a chance constraint involved in these algorithms for the safety. And so here, this is sort of the probability of safety guarantees is sort of being changed from 1 meaning no safety constraint to 0.01, which is 1% of violation of the safety constraints. And you can see sort of regret increases as you want more and more safety. To more and more chances of not violating the power system constraints, basically. What I want to show you is what these safe algorithms do with, and how it's different perhaps with an unconstrained learning algorithm. Here, the goal of, for example, the algorithm I was showing you is try to get the demand to match perhaps a target load profile. The actual algorithm allows the target profile to change every day, but I didn't want to do that, and just for the sake of showing you the result here, the target profile is constant every day. It's that blue curve that's around 60 per unit, if you see. We're trying to get the demand to match that blue curve. Now, an unconstrained learning algorithm may post a price perhaps on day 5 that's that solicits the response that I'm showing in orange, I guess. It's very high, and it's higher than the apparent power flow limit that we have imposed on this problem. And so it's going to try to get the demand to approach the target profile from above, whereas the other algorithm that we are proposing kind of tries to get the demand to match the power profile starting from really low numbers. You see sort of posting really high prices in the beginning because it doesn't know how demand is going to respond. So it doesn't want to risk anything, and sort of gradually changing the price to match the blue profile. So that's sort of the idea of the constrained learning algorithm as opposed to the unconstrained learning algorithm. And so with that, I tried to stick to, I think I'm almost perfectly at 40 minutes, Kate. So I hope it wasn't too rushed. I tried to cut things out to be 40 minutes. We did talk about, safe algorithms for sort of, for cases where we had linear representations of the reward and affine constraints, and we saw some regret guarantees for those cases, but then we saw it's really hard to come up with perhaps similar results in cases where we're dealing with complex representations like power system distribution constraints or power system cost functions that are nonlinear, and then there's context, there are things are different every day, and so on. And so the algorithms we try to study in the second part of this talk were rather sort of practical algorithms with some safety considerations. I want to acknowledge my students. They did most of the work here, and also my collaborator, Christos Trampouloudis, and also the funding sources that helped us do this work. And with that, I want to thank you and ask whether there's any questions.
Awesome. Thank you so much. That was great and very impressive timing. So I'll stop the recording now and then we can do questions.